Hello there, Mr. Sutton here, bringing you the IM3 Honors Chapter 7 Quiz 2 Review Solutions on Trigonometric Equations and Identities.
To solve this trig equation for angles between 0 and 360, we need to first isolate the trig function. So adding 5 and dividing by 5, we have tan of theta equals 1. Next, let's figure out where our answers are going to be. So since this isn't sine or cosine equaling 1 or negative 1, we know we're going to get two different answers for this. So let's figure out where they could be based on what function this is. This is tan, it's positive, and tan is the slope of the angle. Slope of the angle is going to be positive in quadrants 1 and 3, where your angle is going up and to the right. So when we do our inverse trig function, we're going to look for angles in quadrants 1 and 3. To get this now, to get our first angle, to get at least a starting point, we need to do inverse tan of 1. So you can do that on the calculator, or you might know that the inverse tan of 1 is 45 degrees. I'll show it to you on the calculator, though. So here we are in the calculator. Make sure under mode that you are set to degrees instead of radians. If you're in radians, switch it to degrees. And then we're going to do second tangent to get this little tan negative 1, tan inverse, and we'll enter 1 in there. And that comes out to 45 degrees. Now, next, after we get our angle, we should see if we can get a reference angle, because we're going to need it for at least one of these. 45 degrees is already a reference angle, so we don't have to do any special work on that. It's already between 0 and 90. Next, let's find the quadrant 1 and 3 angles based off of this. So quadrant 1, we actually already have that angle. It's 45 degrees. They gave it to us right off the bat. For quadrant 3, we need to use our reference angle and add that to 180 to get quadrant 3. So that takes us 45 degrees past the 180 line. That gives us 225 degrees for our second angle. For this problem, we have secant that we're trying to isolate and get an angle out of. Secant is not one of the calculator button angles. It's not cosine, sine, or tangent, so we'll have to do a little extra work on this one. Let's start by isolating secant of theta, though. So adding 7, we have 18. Dividing by 3, we have secant of theta equals 6. And I don't want to work with secant, so I'm going to use the reciprocal function cosine. But if I turn this into cosine, I also need to take the reciprocal of the other side and call this 1 over 6 instead of 6. So I can write cosine of theta equals 1 over 6. Again, I'm just essentially flipping both sides of the equation. And now this tells us that my cosine is positive, which means that our answers for this are going to be wherever the x values are positive, which is going to be in quadrants 1 and 4 to the right of the y-axis. Next, we need to do inverse cosine of 1 over 6. Do that on the calculator. So we will do second cosine of 1 over 6, and I'm just going to do alpha y equals to get my fancy fraction mode here. So there we go, 1 over 6. Close the parentheses if you want, and that gives us 80.4 degrees. That is already a reference angle, which will be helpful. So now we need quadrant 1 and 4 answers. Quadrant 1, we actually already have that answer. It's 80.4 degrees. We got it right away. For quadrant 4, we're going to need to use our reference angle and go back 80.4 degrees from 360 to get into quadrant 4. Quadrant 4, not quadrant 2. There we go. So 360 minus 80.4. Doing that on my calculator, I come out with 279.6 degrees. To solve this or any quadratic trig equation, we need to break it down into first power trig equations using either square rooting or factoring or some combination of those. So for this one, because I have something squared equaling a constant, I'm just going to square root both sides. Now remember, when you do this, you get a plus or minus because you're square rooting an equation. So I'm going to have the square root of sine squared, which is just sine, equals the square root of 3 over 4, which is radical 3 over 2. So we have a positive version of that. And we also have sine of theta equaling negative root 3 over 2. So now we have two first power trig equations that we're going to solve independently. Let's start over here with the positive root. So we've got a sign that's positive. That means that I'm going to be looking for positive y value kind of quadrants. So that's everything above the x-axis, quadrants 1 and 2. Let's go ahead now and do inverse sine of root 3 over 2. Now, you could do this on the calculator, or you might know that the sine of 60 degrees is root 3 over 2. If you remember that, you don't need the calculator, but you could use it. 60 is already a reference angle. That'll help us down the road. So in quadrant 1, we actually already have the quadrant 1 answer of 60. In quadrant 2, we have a reference angle we can use. So 180 minus 60 will give us a quadrant 2 angle of 120 degrees. That's the first branch. Now we come over here to the second branch. We have a negative sign for this branch. Since that's negative, that means we're below the x-axis in quadrants 3 and 2. We need now the inverse sine of negative root 3 over 2, which again you might know off the top of your head that that's negative 60. If not, let me show you this on the calculator. So we're going to do second sine inverse, and then I'm going to use my fancy fraction here just to make my life a little easier. I'm going to put a negative out in front here. And now up top, I've got the square root of 3. And down below, I've got 2. And close the parentheses for good measure. We end up with negative 60. There we go. Now, that's not quite a reference angle, but it's pretty close. Negative 60 degrees is 60 degrees away from the x-axis angle of 0. So this is just a reference angle of 60 degrees, which we can now use to find the quadrant 3 and 4 answers between 0 and 360. So for quadrant 3, we're doing 180 plus our reference angle of 60, giving us 240 degrees. For quadrant 4, we're doing 360 minus 60, giving us the quadrant 4 angle of 300 degrees, which is essentially just this negative 60 plus 360 to make it positive. For this problem, to solve for this in radians between 0 and 2 pi, I'm going to first get everything over on one side. This is a quadratic trig equation, so I either need to use square rooting or factoring. And since we have this first power term in here, factoring is the only way to do this one. So adding the 1 over to the left side, I have something that I can try to factor. 2 sine squared, I have to split that up into 2 sine and sine of theta. And the 1, well, that's either going to be negative 1 and negative 1 or positive 1 and positive 1. Since this middle first power term is negative, I'm thinking these have to both be negative 1s. So I'm going to write 2 sine of theta minus 1 times sine of theta minus 1. And now I can set each of these factors equal to 0, and that gives me 2 different trig equations to solve. So for this first one, if I add 1 and divide by 2, I can write sine of theta equals 1/2. For this other one, I'll just add 1, giving me sine of theta equals 1. Let's do this first branch. So this means, since we have a positive sign, we're in quadrants 1 and 2, because y values are positive above the x-axis. Doing inverse sine of 1/2, you might know off the top of your head that that's going to be 30 degrees, or you could do it on the calculator, second sine on the calculator. Now 30 is already a reference angle, so we don't have to do anything special to get our reference angle, but we do need a quadrant 1 answer, which also happens to be 30, and a quadrant 2 answer, which we can get by doing 180 minus this reference angle of 30, giving us 150 degrees. Now note that we're going to have to convert these to radians down the road, but I'm just getting all my answers in degrees because I think it's a little bit easier to deal with the reference angles in degrees. All right, this other branch, sine of theta equals 1, this is one of those special cases where you know you're just going to get a single answer. Wherever you have a cosine or sine of theta equaling a 1 or a negative 1, there's only one place on the unit circle those cases happen. So this is essentially asking, where is my y value equal to 1? That's at the top of the unit circle at 90 degrees. All right, let's go back now and make all these radians. 30, that's going to be pi over 6 radians if you reduce this over 180. 150, that's going to be 5 pi over 6 radians. And then 90 degrees, that's pi over 2. For this problem, we just need to list out the big 3 Pythagorean identities. So we have the original one, sine squared plus cosine squared equals 1. And the other two are based off of this by essentially dividing everything by either sine squared or cosine squared and simplifying to trig functions we know. So we've got 1 plus tan squared equals secant squared of x. And the third one, cotan squared of x plus 1 equals cosecant squared of x. And note that in all of these where things are being added together, it doesn't really matter what order you add them in. So this could have been written cosine squared plus sine squared, and we could have also reversed the 1 in the other trig function in these last two. For this problem, we're trying to simplify this trig expression, which is to say we want a single trig function or a single number when all is said and done. All right, so we've got a few strategies for doing this. The acronym PAX kind of sums it all up. P for Pythagorean identities, A for algebraic manipulation, and CS for cosine and sine. Now, Pythagorean identities are going to be tough right now because there's no squared trig functions. Algebraically, there isn't really much we can do in terms of combining or factoring or foiling anything. I mean, we could get a common denominator and move these into one fraction, but not sure where we go after that. So that leaves us with cosine and sine, the last resort move here. We're going to turn everything to sine and cosine. So we've got cosecant, which is really 1 over sine, and then we still have a sine in the denominator of that first fraction. Over here, cotan, that's cosine over sine. Tan is sine over cosine, so that's a big, crazy-looking fraction there. Now we're going to use a little algebra and see if we can combine these in some way. So let's do this first fraction. This is really 1 over sine times 1 over sine if we multiply by the reciprocal. So that's actually 1 over sine squared, which is kind of nice. And then over here, if we do same change flip, we've got cosine over sine times cosine over sine. So this is going to be minus cosine squared over sine squared. Now, the nice thing about this is we have a common denominator. This is just begging us to move this 1 and this minus cosine squared x into the same numerator. So let's go ahead and follow the flow on this one. There we are. Now, where do we go from here? Since we have some squared trig functions, that means it might be time for some Pythagorean identities. Is there an identity that has cosine squared or sine squared in it? There actually is. It has both of them. It's that sine squared plus cosine squared equals 1 identity. And then if we want to, we can rearrange this by subtracting cosine squared from both sides, giving us 1 minus cosine squared equivalent to sine squared. That means wherever I see either of these, I can substitute the other. Well, I'm going to take this 1 minus cosine squared and swap in a sine squared for that. I could have gone the other way. It actually won't matter on this problem. But if I see sine squared over sine squared, well, anything divided by itself is going to be 1. On this problem, we have cotan x secant squared x minus cotan, and we're trying to turn this into a single trig function or number. So there's a few things we could try. Pythagorean identities will make sense a little bit later because we have this squared trig function here, but it's kind of mixed in with all this other stuff, so we're not quite there yet. Algebraically, we can factor a cotan out of all of this, leaving us with secant squared x minus 1. Now, that doesn't always give us what we want, but in this situation, having secant squared minus 1, this is a pretty good thing because we have an identity 1 plus tan squared equals secant squared that we can rearrange to give us this pattern. If I subtract 1 from both sides in this identity, I see that secant squared minus 1 is equivalent to tan squared. So this stuff in the parentheses is really just tan squared. And now cotan, you might remember that that's really 1 over tan. So we can cancel out this tan with one of these tans, and that's just going to leave us with tan of x. Now, at this point up here, you could have changed everything into sine and cosine. You could have really done it all the way up here, and you eventually would have gotten to tan of x. This is just the most efficient way of getting there, but you'd get there with sine and cosine.